All right, let us talk about interference. I've given you a note on this particular topic, and I've also given you the definition of interference. Now, what is interference of light? Now, in the definition of, according to the definition, interference is nothing but the redistribution of light intensity or light energy on a screen due to the superposition of light waves coming from two coherent sources. Now that definition, it may sound confusing to you at the moment because some of the terms you're not familiar with. All right, but I promise you later on, as we go about in this chapter, that definition will become clearer and clearer to you. Okay, now remember first of all that light is what type of a wave? It is a transverse wave. Okay, a transverse wave. Transverse wave is something like this. It has gone something like that, right? So this is a transverse wave where this part is called the crest of the wave. Okay, and this part is called the trough of the wave. Got it? And here there's a line. Okay, the line which passes through the middle. This is the point where the amplitude of the wave is 0. Okay, now what do you mean by amplitude? Amplitude means this distance. This is the maximum displacement of the wave from this point. So that is the amplitude of the wave. Similarly, we can take this to be the amplitude of the wave. Let's take this amplitude to be A1. Okay, so this is the nature of light. It is a transverse wave. All right. Now, suppose if you have two waves coinciding at a point. Okay, if two waves coincide at a point, it may coincide in this manner. Let me rub this off first. It may coincide in this manner. It may go like this. Let's say I have this line. Let's say I have one wave which goes like this, and another wave, the green one, goes like this. Okay, so if you look at this kind of coincidence of the wave, this is called superposition of waves. All right, so when two waves meet at a point, they are said to superpose. They are said to what? Superpose. Okay, so basically superpose means when the waves, they move together or they meet at some point. Got it? Now there are two ways in which the waves there are two ways in which the waves can coincide or superpose. They can coincide in this manner, in which the crest, can you see this crest of the red wave coinciding with the crest of the green wave, or the trough of the red wave coinciding with the trough of the green wave. Okay, now if they coincide in this manner, then what will be the amplitude of the resultant wave? The resultant wave, because if you look at this particle here, the green particle is going in this direction. Okay, it is going in this direction. It is pulling in that direction. The red particle is also pulling in that direction. So basically what will happen to this crest portion of the wave, it will become bigger. Why? Because these two particles are pushing in that direction. So the resultant wave will be something like this. It'll be something like that. I think I didn't put this part. Okay, redraw this. It'll be something like this. You see, what is this white color? the white color, this is the resultant wave. Got it? Now if you look at these two waves, the green wave, its amplitude is from here till here. Let's call this amplitude as A1. The red wave, its amplitude is from here till here. Let's call this amplitude to be A2. And the resultant wave, you can see that its amplitude is large. Let's call this A. In fact, the amplitude here is A1 plus A2. Okay, it is the algebraic sum. The algebraic sum, not algebraic, the vector sum of these amplitudes. So because the amplitude of the resultant wave is large in this case, then what will happen? The intensity, we know that intensity is proportional to the amplitude square. And since A is large, since the amplitude of the resultant wave is large out here, then in that case, the intensity also will be large. Okay, what do you mean by intensity large? Intensity large means, you know intensity, right? If you have a bulb of 10 watt and a bulb of 100 watt, which one is brighter? The one with 100 watt will be brighter. Intensity means the brightness, basically. Okay, so like I said here, because these two waves are coinciding, are superposing in this manner, the amplitude of the resultant wave here is large. And if the amplitude is large, what happened to the intensity? Intensity also will be large. So a point having large intensity, this is called a bright point. Bright point. Okay, later on we will introduce the term fringe, but let's stick to bright point for now. So this is one way in which the wave can superpose. The second way is this. On this line, then you have this green wave. Let's say this green wave is like that, and you have the red wave. Can you see? So you can see here that the crest of the green wave is coinciding with the trough of the red wave. Similarly, the trough of the green wave is coinciding with the crest of the red wave. So in this case, what will happen here? You will notice one thing. This particle is pushing in that direction, whereas the particle of this green wave is pushing in that direction. So it's like they are pushing in opposite direction. So because they are pushing in opposite direction, the resultant wave will have an amplitude which is equal to A1 minus A2, or A2 minus A1, whichever one is greater. So here we are assuming that A1 is greater than A2. All right, so A1 here is the amplitude of the green wave, that is A1, and A2 here is the amplitude of the red wave. So what is A1 minus A2? So basically A1 minus A2 will be less, will be small. Yes or no? So where will the and if we have a vector like this, A1 minus A2 vector, then in that case the resultant vector will point in the direction of the larger vector. Yes or no? We know that. So therefore here you have the two vectors, A1 in this direction, A2 in this direction. So the resultant will be in the direction of A1. So you get a wave in this, like this. Okay, so this is the amplitude of the resultant wave. The amplitude of the resultant wave, and we can see here that the amplitude of the resultant wave is small amplitude. And if the amplitude is small, what kind of a point are we getting? What happened to the intensity? The intensity also will be small, and we are getting a dark point. Okay, we are just assuming that A1 and A2 are not equal. But suppose if A1 and A2 are equal, this is a very special case. So you have a green wave like this and a red wave also like this. You can see that their amplitudes are equal. Okay, so what will be the resultant wave? The resultant wave will be along this line. It will be along this line. Okay, so that is the resultant wave. It is not a wave only. Got it? And so what is the amplitude of the resultant wave? Amplitude of the resultant wave will be 0. So this will be the intensity I will be 0. So what kind of a point is this? This is a dark point. Is it clear here? So this is the basic concept of interference of light. So you have to understand this concept very, very nicely. Okay, the interference of it all depends on this concept. Let me just repeat. So basically it depends on how the waves are meeting at a point. If they meet like this, crest of one coinciding with the crest of the other, then in that case the amplitude of the resultant wave will be large. And if the amplitude is large, intensity is large, which means that it is bright. You get a bright point. But if they coincide like this, the crest of one coinciding with the trough of the other, then the amplitude of the resultant wave will be small. And if the amplitude is small, intensity is small, and that gives you a dark point. In this case, if suppose the two amplitudes are equal, let's say this amplitude here, the distance from here till here is equal to the distance from here till here, then in that case A will be 0. A will be 0 means there is no amplitude, so there I will be 0, and you get a perfectly dark point. Okay, and one thing which is important to note out here is the phase difference, delta phi. Okay, delta phi here is 0 degree, right? 0 degree, because they are in phase. They're said to be in phase. These two waves are said to be in phase. They are vibrating together. Okay, this point and this point, they are vibrating together. That means when this green point is going up, this red point also is going up. When this green point is going down, this red point is also going down. So that means they are vibrating together, which means in phase. So when they are vibrating in phase, the phase difference delta phi is 0 degree. And here, what about the phase difference here? The phase difference here, this is vibrating up, this is vibrating down. The phase difference here is 180 degree or pi. Okay, right, got it. Now on the screen, suppose if you have the two waves, two sources of light. Let me again take the green and the, let's say I have one source of light out here. Let's say this is S1, then you have the waves going in this direction, right? And let's say this is a screen. Okay, and another wave, okay, so you have one source going in that direction, another, one wave of light going in that direction, another wave of light going in that direction, and they meet at this point P. Okay, now all you need to do is look at this point where they meet. How are they meeting? Crest with crest or crest with trough? It's very evident from here that crest and crest are meeting. So what kind of a point is this? This is a bright or a dark point? This will be a bright point. Got it? And then somewhere here they will meet like this. Okay, they will meet like this. Right, now at this point Q, just look here, this point Q, how are the waves meeting? The waves are meeting, the crest and the trough is meeting, so this is a dark point. Okay, then again you have like this, so this will be a bright point again. This will be a dark point. So on the screen you are getting what? You are getting alternate bright, dark points. Yes or no? So these bright and dark points, they are called what? They are called fringes. Sorry. They are called fringes. Okay. So basically from these two sources of light you get the intensity of light is getting redistributed. Okay, if you have just one source, if you have just one source of light, let's say I have the screen like this and I have just one source of light, source S, then I have the light going in this direction. Okay, now if you look at the entire screen here, it is uniformly illuminated. Uniformly illuminated means the intensity, the brightness of the screen out here is the same everywhere. Imagine you have a torch and you face the torch onto the wall, you'll see that the wall will be bright everywhere. Yes or no? This is because you are having only one source. But if you have two sources of light like this, then the waves, it interfere, it superpose differently at different points on the screen. Can you see? Differently here, how does it superpose? Crest with crest. Here, how does it superpose? Crest with trough. And then again you have crest with crest, crest with trough. So because of the superposition of light waves coming from two coherent sources, what kind of sources? Coherent. Coherent sources. Okay, I will give you the definition of coherent sources later, but for now you just take it for granted these sources are coherent sources. So with the due to the superposition of light waves coming from two coherent sources, the intensity of light gets redistributed. You get a point where the intensity is high, that is a bright point, and then followed by a point of low intensity, that's a dark point. Again you have a point of brightness, okay, a bright point, and then a dark point, so on and so forth. Got it? So this phenomenon of redistribution of light intensity or light energy on a screen due to the superposition of light waves coming from two coherent sources, that is called interference. Okay, so that is the meaning of interference of light. Please read the definition nicely. Okay, so in the next lecture I will discuss with you the Young's double slit interference experiment.